Hello everyone, this is Vladimir. I have built yet another electronic astronomy tool, and this is a little demonstration for those who want to use the source code which I have published on GitHub along with the schematics of all the electronic devices and connections. If you want to build this tool, this video might be helpful for you to understand how it should operate once built. This device has an accelerometer inside this big box and a magnetometer inside the small one, as long as several 7-digit LED displays and a rotary encoder knob for user interface. So it works like this. When I turn it on, it gets the Arduino inside going. It loads some data from the EEPROM memory that has been stored from previous use. And then it shows me two readings. The left reading is a compass reading, meaning this compass, when headed north, it will show me a 0 or 360, and as I rotate the compass, it will show me a reading that gets to 90 when I'm aiming east, 180 when I'm aiming south, and then 270 when I'm aiming west. So this is a basic electronic compass. It has 1/10 of a degree resolution, which, as you can see, is not really that stable because electronic compasses are just like that. But it could be useful enough for a basic polar alignment of a telescope, and the extra resolution, which is one more digit than you can find on smartphone apps or analog compasses, it's somewhat useful to do polar alignment. The second reading is the typical inclinometer. If I raise this and change the inclination of the box, it's going to show inclination going high. So you could use this as the altitude reading and the optical toolbar for setting circles and aiming a telescope. It's very basic, typical inclinometers work just like that. This one has controllable brightness. By rotating this knob, I can get it to be darker or to be as bright as I want, especially useful when I am using this device at night. I don't want it to affect my night vision, so low brightness is useful for that. Now the two readings can be zeroed. If I click the knob, then I am zeroing this reading so that I can adjust true north to whatever value I want. I can raise the value or lower it to whatever my local magnetic declination is, or wherever true north is. I can put this in the azimuth layer of a telescope and align it with Polaris to get the best possible true north reading. And when I stop moving it, after 10 seconds, it will store the offset that I just adjusted to the internal memory, so that it will persist even after the device is powered off or the batteries are removed. So that's how you zero the compass reading. And if I hit it again, I can zero the altitude reading, which can be used to compensate for small misalignments in the enclosure of the device. I could attach it to the optical tube of the telescope, aim to a star with known altitude value, and adjust it, zero it to the exact value that it should have, so that the reading can be more trusted. Besides that, the device has another mode of operation. I get these two readings. The left reading is a level. It works just like a digital level. So if I incline it towards me or away from me, it will change the reading. The right reading is the level in another axis. So if I incline it right or incline it left, it changes its value. So this is useful for a quick leveling of a telescope that requires to be leveled in order to be able to track. This is, a little bit more accurate than the typical bubble level. It's convenient mostly. It's not as necessary, but sometimes it can be difficult to use the bubble in a level in the dark at night. So this one is quite convenient to be able to see two different axes and level the device along the line of them. It can be zeroed as well. If I click this, I can adjust the value of the zeroing for this axis. If I hit it again, I can adjust zero the device for the other axis, so that I can be absolutely certain that it is level. It will also store the offsets for both adjustments that I have made in the internal memory, so that after I power the device off, it will still remember what their offsets were and which is the true horizontal position. So this is the device. It's very neat. It's useful for astronomy purposes. It's not groundbreaking, and it's not something that has not been made before in one way or another, but it can be useful. And if you're interested in building yourself one like this, I have published all the schematics and source code in GitHub. So enjoy.